So I've prepared two predictive maintenance cases that we've been working on, which is, I think, fits quite nicely now because we're also dealing with a bit with computer vision, which we saw earlier as well. Something about track geometry, and then also something about lifecycle management. So how do we fit the models that we built together to create one big picture? But I'll start with a short introduction, some key figures, some challenges, just to give you a broad overview about what ÖBB is, ÖBB infrastructure. So roughly, we are dealing with around 5,000 kilometers of rail network, which equals to around 10,000 kilometers of tracks. And roughly, we are investing 3.3 billion euros every year. This includes everything from renewals, maintenance, catenary track, so the whole picture basically. And so the way ÖBB is structured is that we are also split into separate parts like Personenverkehr, rail cargo, and then the infrastructure part where I'm based basically with my team. So just a brief overview of our network. As I said, we have 5,000 kilometers of track. I really like our network. Not so much, it doesn't look like a real network, but we basically have the alpine areas where we just have like a few northern southern corridors, one eastern western corridor. But here in the vicinity of Lower Austria, around Vienna, also around Graz, Klagenfurt, and Upper Austria, where we have the basin areas, we also find like real network structures, basically. But it's very heterogenic, and that makes it very interesting to deal with, because whatever you develop might work on one part of Austria and might not work in another part of Austria. So one of the big challenges we are facing, and sorry, this slide is still in German because it was a picture, I couldn't edit it. Even ChatGPT could not edit it, so I have to tell you what it says. So basically, it's about our capacity, which we have to double within the next 15 years up to 2040. Sorry. So we are part of the mobility turnaround in Austria as ÖBB infrastructure, and we are really trying hard to push up the capacity and to double the capacity up to 2040. Much of this capacity increasement will have to come from the infrastructure part. There are some parts that come from the wagon materials, some parts from the operation of the digitalization part, but most of it will have to come from the infrastructure part. And so in my team, we have some nice sensors. We've heard about very small sensors. Our sensors are a bit bigger. They're 26 meters long and weigh around 80 tons. They look like this. We are dealing with track measurement trains that cover the whole network. We have an obligation to make sure that our network is safe. And in regards to the Euronorm regulations, we have to do track geometry measurements like a few times per year. But we also have around 150 different parameters that we take on every measurement run. We take the parameters every 25 centimeters up to a maximum speed of 250 kilometers an hour. And as we heard in the discussion in the morning, the difference between other measurement possibilities is that this is a measurement that is done under load. The two track measurement cars are also equipped with LiDAR scanners, and roughly we cover every track and the continuous main tracks between 1 and 6 times a year. So that's more or less the time series we get from our data. The nice thing about these track measurement vehicles is that we have consistent time series for 20 years. And this is like a huge benefit. It's such a huge benefit, and it really enables us to work with a lot of data. Just to give you a brief introduction, so that's how they work, how they look like. So these are the two track measurement vehicles, the so-called rail checkers. Here's part of my team on board. So everything is done up to 250 kilometers an hour. Yeah, we have a video system on the ground, which you will see later, which produces very nice pictures with millimeter resolution of the ballast and the track bed. We have the driver's view cameras. We have LiDAR scanners on board that we use for a lot of information. Gauge measuring, track geometry measurements are done every 25 centimeters. Most of the data is cleaned and processed on board, and later on during the data management we enable the data to be provided to our users a few days after the measurement run. Of course, we have to put AI somewhere, so here it is. Whatever that sentence means, I don't know. Our communications department found it was very smart. Okay, thanks. What is important for our customers, which are the track masters, is that we provide all the data we have from around 20 years on a platform that was built in-house, where we host about 2 billion data points with about 500 terabytes of data, so half a petabyte of data, which users can access with one click. And all this is the base for the planning of maintenance and renewal works of the tracks. So whatever has been done on the tracks, somewhere the answer lies in our data. So as I said, I've brought two practical use cases. The first one deals with computer vision. So here we're looking at insulation joints. Insulation joints are more or less the smallest component I think we have to deal with on the track. It's a 5 millimeter gap in the track. We'll see it later on a bit bigger as well. The idea is it's part of the signaling system, and it's a very critical component regarding availability of the tracks. So if there's a damage, and there's current flowing from one track, from one rail to another, then the signaling thinks there's a train on the track and blocks the track. So then somebody has to get outside, a track master. They know somewhere where the fault is, but still they have to look for the fault. They have to detect the fault on the insulation joints and set the appropriate measurements. And during that time, the track is not available for the traffic. So here you can see what it looks like. So these are the images from the track component video system, also taken up to 230 kilometers an hour. And if we zoom in, that's what we're looking at. It's just this small 5 pixel wide gap in the rails. So what we tried to do is we wanted to build a classification system. So first part was that we tried to localize the insulation joints. We're talking of about 40,000 insulation joints, 10,000 of which we know that we passed them with the measurement trains. And we wanted to build an AI system for, as I said, also automatic classification. So first we had experts. We were talking about labeling boxes early on. So these experts had a lot to do with bounding boxes and setting labels. So they labeled 10,000 insulation joints. And as you see on the lower left corner, expert 1 and expert 2, do they agree? Not really all the time. So we see that the very bad insulation joints are in the right lower corner, but then in the upper left corner are the better ones, the good ones. Then in between, it's a bit blurry. So yeah, that's one thing you have to deal with is the human component, and you have to deal with differences in expert opinions. But we've built a model from that data, which is very good at detecting the very good insulation joints and quite good at detecting the faulty ones. And this is already a big effort. So the whole thing has been implemented in our Messtechnik application, which is an online-based application. So basically, you get a list after every measurement run, which gives you a classification of the insulation joint. And then on one click, you can, not this click, this click. And then on one click, you can enhance the image and see what's actually going on and compare it with other measurement systems. Yeah, the way we integrated it was we made sure that we follow the human in the loop process, which means that we have the images, we do the model, we deliver the whole thing into the Messtechnik application to the users, and the users must document if they do measure, if they set some measures. So we also get the information back again, but they also have the possibility to rate and to make corrections to our classification, which will at a later stage go back into the model update. And this is very important. It's a small feedback button, but it gives much more trust to the users, and we learn also from our mistakes. So this was use case number 1. This is use case number 2 I've brought. We are looking at forecasting track geometry on a network-wide scale. So the idea is to have a quantitative forecast of the future track geometry throughout the whole network. The base, as we've seen, are the measurements that come from the track measurement cars. And just the business case behind it is basically that we're talking about 700 million euros a year that are going to maintenance or renewal activities in the track. So the idea is also again that through the implementation of the preventive measures, that we also can see that disruptions are being reduced and that closures of tracks also can be reduced, of course. So basically what we are doing is based on irregular time series of the track geometry measurements. We generate models. We set up a prediction. We make sure that, and this was more or less the biggest part, getting the data clean. We've heard it in the earlier talks that it's a huge issue, but we're quite sure that our data is really clean, and we have time series of about 20 years that help us to find those patterns. Then of course the models are created and also validated, and we try also to find a possibility to show the results in such a way that our users can also draw the right conclusions from what we calculate. And this should be the basis for the decision making for all the maintenance planning and the renewals as soon as it fully operational. So what is already operational is this here. So we have an application. You can zoom in. This is the whole network again. We just show it's very simple. We try to keep it as simple as possible. We're looking at the standard deviation of longitudinal level, which Stefan also explained earlier on. And I guess you could guess, but the darker the green, the better the track quality. Yeah, the more orangey or red parts, the better it is. This is the current state. I can then zoom in to a spot that I'm interested in. These are the current measurements. But then, of course, the track masters don't so much care about the current measurements, but they want to see, okay, how is what's going on that track. So that's why we calculate for every 5 meters of our tracks, we do those prognosis. And so what they have is in the application, they just have a time slider, which you can either set into the past or into the future. And if you push it to the future, then you'll get for that section that you are looking at the forecast of the track geometry for defined future points in times. So which means you keep on sliding to the right, you see that unfortunately everything just gets worse. Nothing gets better. Yeah. So, but even that is not the question that the track masters have. The actual questions they have in mind is how long do I have till I have to set a specific measure? So what you can do is you look here at this. This is called the tamping prognosis. So how much time do I have until I reach the intervention threshold of the standard deviation longitudinal level in years? And you can push it on, and you see there are some red hotspots. Then you can even filter, and you say, okay, I'm only interested in the measures I have to take in the next 1 to 5 years. And then you see the exact hotspots on the network in that area you're looking at, where from the prognosis, we think there's something to be done. Then, of course, you can go into the detail, and you can look at this 5-meter sections. This is like how the typical longitudinal standard deviation signal looks like. So it's getting worse, which mean higher values. Then we see the tamping getting worse, tamping getting worse, tamping. And then at the end of the scale, you see the prognosis with the prognosis intervals as well. So I have something to show you. Here you can see how happy our track masters are when they use it. So basically just a web-based application. You just go there, you zoom in. Somewhere in Vienna, you see the actual track measurement. He's very confident. Then you push the slider into the future, and then you see some red spots down there. But Roland is still very confident because he knows that he has set the right measures. He's not an actor, by the way. He's a real track master. But we really try, as sophisticated everything in the background is, it's important that our users don't feel it. It should be as easy as that. There's one slider where you can change the time, and then you just see from green to red what's happening. So in the meantime, we have been working on other things as well. Stefan also mentioned it earlier. One thing that we are really digging much and very deep into is the cause and effect models. So we really try to increase, to import new parameters, which not only show us the condition of the track, but also show the whole influences that the track receives. And this goes from traffic load, past maintenance activities, everything that is subsoil, geology, We have huge impact of precipitation, which we see. We have discontinuities and many more parameters that play a role and play a vital role in dealing with cause and effect. And the idea is always that whatever comes out of the pipeline is just a recommendation. So it's always the human or the track master that has the last word. The idea is for all our forecasts, we want to be able to answer 3 questions. Which measure do I have to set at what point in time and at what place? So it's those 3 questions that we try to answer as good as possible. I think we're quite good at answering the lower 2 questions already. Tell me the time and the place I need to set an activity, but maybe we still have to work on the right measure. So one thing we introduced now is the load. So you can, again, the same stretch of track we've been looking on earlier. You just click onto the track you're interested in, and then you see the track load in, this is tons per day for the last, 8 years now. Yeah? You see some spikes, and not having that data might mislead you in not understanding correctly what the degradation that you see from the measurements actually means. So it's important to make sure that that's also being based in data. Another thing Stefan mentioned, turnouts. We are really digging deep into turnouts because they are so critical in the infrastructure. We are getting much support from Stefan and his team. There's a lot of literature giving us the methods we need to implement, but then implementing this in a production setting is always a different kind of story, because now we're not dealing with 20 or 40 turnouts, but it's 30,000, and then we want to make sure that everything works the way it's expected. So we've started doing some steps forward here. So we, slowly progress. So for the third point, how does this all fit into modern lifecycle management as we do it? So how do we get from those hotspots we see in this application into a holistic integrated action planning? So at ÖBB, we have 3 levels, basically 3 dimensions of lifecycle management. The first one is the lifecycle engineering. Then on top of that, the lifecycle costing, and then on top of that, the lifecycle management. And at the end of the day, we have to guarantee that the security is always there. That is our main concern. That we optimize the availability, of course, of our tracks, and also that the economic efficiency is optimized. So if we look at the life cycle engineering, that's basically forecasting the technical condition of components or parts. This is just what I've shown you before, whether it's the insulation joints or whether it's the track geometry. But on top of that, we also need models for other components like the catenary or the bridges or the tunnels. So there are a lot of model stuff that have to come up with the next few years. So from that step, the next step is looking at the lifecycle costing. So now we are doing the technical and economic evaluation based on the lifecycle costs for each of the assets we were looking at. So in this case, this is a piece of track. So I look at the degradation of the sleepers, the degradation of the rail, and add the costs up for the maintenance. And then I get the lifecycle costs with an optimum somewhere. And then the last step on top of that is now to include everything in the lifecycle management, where we also look at the synergies between different assets, not only looking at tracks, but also looking at catenary and others. So this is the holistic optimization of the asset availability. At ÖBB, we have a separate tool for that, which is called the LCM Assistant. So basically, here again, this is the same piece of track which we saw earlier. You can zoom in. You get for all the assets we have there. You get the life cycle costs, and from that on, you can form your package of maintenance activities or renewals that has to be done, and it can give you the optimal point from a life cycle cost view to deal with the works. So next steps. I don't think that my team or I will be replaced by AI soon. We still have a lot of work, hands-on work. So one thing which we heard earlier was we want to find the root causes, not only the symptoms. This is essential. I can only set the right measure if I know the right cause. So this could be something like that. So if I look at the piece of track, where does the degradation come from? Does it come from the load, from the subsoil? Does it have to do with the precipitation in the time that has been between two measurements? Then also one thing that was mentioned earlier, we need dynamic intervention levels for maintenance. That's our chance to challenge what we are using right now. One focus, turnouts. As I said, there's been a lot of work going on here. And we have to make sure that we earn the trust of our users. We've seen it with other technologies that come quickly and leave a lot of mess, and then it takes 10 years to clean up afterwards. And that's something, a pit I don't want to fall in with the things we do. So sometimes we take our extra time to make sure everything is correct and accepted by our users before we hand it out and set it into productivity. Then adding on top, if we can do all that, we also want to go into simulations and scenarios. So especially the lifecycle management part. What does it mean if we close down a line? What does it mean to the other lines? If we distribute the load, how will the degradation change there? So there's also a huge theme that deals with all the complexity that we bring in with when we change our maintenance strategy. So at all we see for us it's essential that we integrate all the predictive maintenance models or degradation models very closely with the overall life cycle management that we are doing. And I don't know whether that exists, but maybe it's something that we try to build. It's an intelligent maintenance decision support tool kind of thing. Thank you so much.